Hello everyone. Welcome to the second part of FTC 731's Intro to Programming Strange. Today we will talk about subsystems, PID control, and lastly, calculation classes. Without further ado, let's get right into it. So, what are subsystems? Well, subsystems, in practical terms, are classes in separate packages from op modes and are used by op modes. These subsystems tend to serve specific functions and have classes unique from one another. They can serve purposes from a wide array of things, such as performing calculations, assigning robots specific controls, and so forth. Subsystems are especially convenient because you never have to rewrite the entire infrastructure for your methods or code used in your subsystem again when used in another package like your auto op modes. You can in fact just call an instance of it and call the methods from your subsystem classes from there. Don't need to rewrite everything from scratch. They also make your code very easy to read by other programmers rather than a whole bunch of Java projects I've seen where absolutely everything is just compact in one class with no organization. Basically chaotic junk just stuffed right inside one bin. Now, to briefly showcase how exactly we as a team structure subsystems for our auto, here's a sort of nutshell diagram to illustrate. Yes, it's very simple, but it does get the idea straight. We tend to have three types of subsystems: calculations, mechanisms, and sensors or localization. The calculation subsystem classes perform all the sort of necessary math and physical calculations for an auto. That may be turret calculations or hood angle to get the perfect shot into the goal. Mechanisms can be simply just put methods that turn on the flywheel or close the gate or whatnot. We make them a subsystem here because it makes start mode more readable and organized. In this case, for our autonomous programming for this 2026 season, we as a programming department decided it'd be best that we combine the sort of the calculation and mechanism subsystems into just one sort of categorical class. So it'd be best to keep them separate, but most often than not, you'd find it more practical to just combine the calculations and mechanisms together. And so the last subsystem here is what we use is sensors or localization. If you're confused about what the word localization means, it is essentially a process that allows the robot to know its local position. That is to say, where it is positioned on the field, what its orientation is on the field, and so forth. Sensors include the Limelight 3A, which is essentially a very sophisticated camera that allows the robot to track specific distances away from an April tag, which is to say, it's just, to put it practically, a QR code scanner that, when scanned, tells the robot what distance they are from it, and thus can be manipulated to tell the robot what distance it is away from the goal. So I'm going to showcase some Android Studio stuff. So in this case, from our Pedro pathing op modes, we have a subsystem package, and we have a whole bunch of subsystems here. For this subsystem, it's pretty short. It is a mechanism subsystem. In this case, it just allows us to set the intake motor on, or just to close the transfer wheel or whatnot. This one's also short. This is for the outtake. We open the transfer and then we turn the intake off, of course. We also have a timer here just to sort of establish how to make that wait function, to make it wait a certain amount of time. And here's the Limelight. This one we did not make. We actually got it from FTC Team 10195. Ethan, he's also great programmer. He is no longer here with us. He has already graduated the college, but he lent us this code and it's absolutely amazing. And one pro tip for FTC programming: use a lot of resources. I mean, I don't say stealing, but I mean borrowing, just borrowing a lot of code. I mean, sharing is caring. Let's be real. And so we have the AMI mechanisms, which is all the calculations. And this includes some of the mechanism stuff as well. As we can see, we have a set velocity function just to set the flywheel at a certain speed. And of course, this output calculation that I will get to at a later slide. Now that we've talked about subsystems, now we can talk about how some of these subsystems are implemented. And that has to deal with PID control mechanics. So PID is an abbreviation for proportional, integral, and derivative. Now, how I like to think of PID control is that of a car brake. When you step on a car brake, you can slow the car down at any pressure your foot lays on the brake. You can slow the car a little bit faster, maybe even more faster, and then very abruptly. Right? You can control at any braking point. So exactly like a car brake, an FTC, a PID control system is simply put a mechanism that allows a specific device to maintain a set target parameter or specification, which can include height, speed, angle, and whatnot. Although, when it comes to practical use, our team and most other programming teams for that matter mainly rely on P, or the proportional part of PID. And that number is usually in the hundreds or thousands place, so it is very, very small. Now, what if you didn't use PID? What if you just wanted to say, well, I'm just gonna set my motor speed at 0.85 without a PID control system? Well, without PID, it is almost nearly impossible to have desired fractions of a target specification like speed, because without PID, the system tends to severely over or undershoot and believe that, hey, this motor speed is at 0.85 when it is on the max, or heck, it might even be over the max and overstrain the motor. That is why you tend to have clamping systems for every PID control system, just in case and for safety reasons as well. This is exactly why PID control systems are so useful and so necessary. They allow for precise control over any target parameter, from servo rotation to motor speeds to nearly whatever you can think of. And fortunately enough for us, for a majority of FTC programming, motor and servo encoders have built-in PIDs. So if you initialize a servo or motor with run using encoder, you can just set the motor or servo to whatever value you want, since an encoder already has a built-in PID system. However, in the case that your robot does not have an encoder, it's actually fairly simple to code a PID control system. So to give you an example, I will change on Android Studio one of my flywheels. For this flywheel, it only has embedded PID control because if we go into our initiate section, it has run using encoder. What if we don't do that? Just remove this one. So it just defaults to not using encoder. Well, now I can't just set target velocity. It's going to severely undershoot or overshoot. So instead, I'm going to remove this. I'm going to leave it blank for now. And I'm going to include a second constant that we will call private double KP, which is our KP constant, and we just give it a very small number like 0.0001. And so, from here on out, we just, in order to create a PID control system, all you need to do is get the current velocity value, which is, I'll just remove this. Actually, no, this one's actually necessary. Double current velocity 1, get velocity, and then we need an error statement. So double error equals to current velocity 1 minus target velocity. And so we also need double power. You can name it whatever you want. Equals to error times my KP. And then we just have power equals to mat.max of negative 1.0, mat.min of 1.0, and this is just your power. And then here, we can just set velocity to just be power. And since the flywheel power should be in a loop statement, the flywheel will continuously ramp up in velocity until the error constant becomes extraordinarily small, and the flywheel just maintains its target velocity periodically. I mean, that's what we see here, right? When we take the current velocity, flywheel, this is a method from the FTC documentation. We can get the current velocity. We take the error, which is just subtract the current minus the target, and then we just multiply that error times the proportionality constant, and then we take we take the max of this. So if we're reading it as a computer, we take the minimum of this first. So whatever's greater. So actually whatever is less. So let's say power is let's say we have a current velocity of 350 and then a target of 750. So that gets us about 400. 400 times your current times your KP constant, which is about I think 0.4. So 0.4. Well, that's the minimum, and the max is 0.4. So it sets the power at 0.4, and then so that means it increases the velocity by 0.4, and once it increases its velocity, it slows down because the error decreases, and once the error decreases, it slows down even more and more, and when it completely stops, well, air resistance gets involved and all that, so it slows down. And if it slows down, it's going to pick up more errors. So it's going to pick up the pace, and it's just going to sort of periodically maintain that sort of average speed. So now that we have covered subsystems and PID control, the last topic that we have for today are calculation classes. For a majority of autonomous programming, to make our team develop a good auto, we needed to implement some sort of math in order to get the robot to shoot efficiently and effectively. This can include calculating the target angle away from the goal as it moves, the flywheel speed, and of course, the hood angle. And I know what you're thinking. Our team made an aimbot, is what you're saying. And if you did think that, you'd be right on the mark. And just to reiterate, keeping calculations as a subsystem is highly recommended to avoid making your upload too cluttered and hard to read. To give you an idea of some of the calculations we need to perform, I'll show you how we calculate the aimbot for our robot's turret to auto-lock onto the goal. So we'll pull up Android Studio again, and this is actually in the same class, which is our calculate turret position. And so first, we get our target position, which is basically just the goals, the goal positions. So we subtract the goal positions from our current robot pose, which we can just get the X coordinate and get the Y coordinate off. And once we do that, we take the angle of it, which is just the arc tangent. If you look back at the slide, you can clearly see it here. Y goal minus Y bot, X goal minus X bot, arc tangent of that gets you your angle of your target. Now back to Android Studio. Now, once you have the angle to the goal, we need to calculate the angle difference, so we know where the turret points versus the robot. Right? Because your robot can be at a certain angle, let's say 45 degrees, and then your turret can be a slightly, extraordinarily different angle, right? Because when your robot moves at an angle, your turret also moves at that same angle, so you need to compensate for that. So you just have the angle to the goal and subtract it from the heading of your robot pose to sort of normalize it. And then we normalize it even further and say that, make it more simplified, right? If you know a little bit of pre-calculus, you would know that, or maybe even Math 3, you would know that values from 0 to pi and 0 to negative pi are basically the same thing. You don't want to have, excessive values where you have 3 pi over 4, because you can that's just saying you're just rotating in the opposite direction pi over 2. Or in this case, 90 degrees. So rotating 270 degrees one way, it's just saying I could rotate 90 degrees in the opposite direction. So normalizing this, it's just saying, what is the shortest angle I can rotate at to achieve this target angle? And so that does the math here. And so once we get that angle, we can just convert it into a silver range, which is strictly bound at 0 to 1. And so once we have the total rotation range, it highly depends on the solver you're using. For our robot, it is about 300 degrees, and of course we convert to radians because code loves radians. And of course we need to enter some values here, which is the center is 0.5, and then of course the solver scale, which is just divide 1 over the total rotation range, which is, by the way, in radians. And so to calculate the final turret position, we just add the turret servo center, which is just away from the center of your robot. It depends on how you place your turret servo. And then you add that to your angle difference times your radiance to servo scale. And once you do that, you literally have the set servo position number to put on your servo, so your turret can just automatically get to that angle. And of course, there's a safety clamp, just in case you don't want to go too out of bounds, stretch your servos and whatnot. So yeah, you have now reached the end of our Intro to Programming Strange series. I hope you get the chance to watch the other amazing videos by my other programming department members. And as always, see you soon!